Okay, so let us continue. So where did we leave? So we discussed that there is this primal problem for the max margin formulation and dual problem. Like, so you would solve the primal when you have like more data points, right? Yeah, where you will solve the primal when you have more data points than the number of features, and you will do this solve the dual when you have more features than the data point, right? Okay, but there is also this additional advantage with the dual formulation, which we just discovered, which is basically in the case of dual formulation, because of the Kkt conditions, like we see that for most of the data points, an is equal to 0, right? So an an is not 0 only for those data points in the margin, right? So, or in other words, when I compute my classifier like this, in the dual classifier, right? So even though the summation is over all the n, I could replace this summation. Okay, so I could actually replace this summation and say y of x, okay, is equal to, let's go back. So this is summation over n, right? So instead of that, I could say summation over n belonging to S, where S is the set of support vectors, right? Like, so it's a set of data points for which the constraint is active, okay? And you would just write here an tn kernel of x xn plus bias. Okay, now this is a much lighter version of the model, because you don't, even if you have 1,000 data points, you might only have 10 support vectors. Okay, now you throw all the other data points and just keep those 10 support vectors. Okay, is that clear? Now the only question that is left here before we wrap up the dual classifier is how to get B, right? So there's an easy way to do that. Remember that for any support vector xn, we know that t of n multiplied by y of xn is equal to 1, right? So t of n multiplied by summation over n belonging to, let's say m belonging to S, am t of m kernel of xn xm plus b is equal to 1, right? Now I can just solve this equation to get the value of b. So to get the value of b, all you have to do is like just take one data point in the support vector, solve the linear equation, and you're going to get the value of b. Is that clear? Okay. So now I think that is that concludes our discussion on like both the primal and dual versions of the max margin classifier. Okay. Now we are going to take a step back and try to understand what is the error function that this max margin classifier is trying to minimize. Okay, so what is the error function that the max margin classifier is trying to minimize? Okay, so I'm going to directly write the error function here, and then I will explain why that is the case. So it's basically summation over n is equal to 1 to capital N. I'm going to define a new error function, E infinity of y of xn t of n minus 1 plus lambda times w squared. Okay, where E infinity of z is equal to 0 if z is greater than or equal to 0, and it is infinity otherwise. Okay, so now what is the first term? The second term, we already know that, right? Like, so if you go back to the primal or dual formulation, like let's go to the primal formulation, you see that the second term is based on the function that you're trying to minimize, right? The first term is actually based on the constraints that you have. The constraint is T of n, y of xn is greater than or equal to 1, right? So basically, this error function, E infinity, is a hard version of defining the constraint. So this error function is going to be infinity whenever the constraint is not satisfied. And when the constraint is satisfied, it is 0. Okay, so this basically, it ensures that the constraints are satisfied. Okay, so note here that the value of lambda doesn't matter. As long as lambda is greater than 0, that is enough. Okay, okay, so now we will come back to this error function again, probably towards the end of this lecture. Okay, but for now, let's see how this algorithm works in practice. So here is an example where you are classifying between like green and red circles. Okay, so now you can see actually two lines, almost overlapping lines here. Okay, so the first line, the blue line, is basically the max margin solution, and the red line is your logistic regression solution. Okay, and you can see that the blue line exactly is in between the two classes, and in the green class you have one support vector, and in the red class you have two support vectors. Totally there are 3 support vectors. Okay, now you could try implementing Perceptron and the max margin classifier. Now the biggest advantage of max margin classifier, like when compared to Perceptron, is it is going to give you always a unique solution. Unlike Perceptron, which depending in the case of Perceptron, like depending on where you start, right? Like for example, let's actually guess what would Perceptron do if I start with a line like this. If I start with a line like this, then this line is going to move slowly, right? Slowly like this. And the moment I reach, sorry, that's a bad example. The moment I reach something like this, now that would be my Perceptron solution, right? Like because the moment I reach here, it is 100%, so I don't need to move anymore, right? So on the other hand, you can see that similarly, if I start my Perceptron from here, then it is going to stop somewhere here. Okay, these are bad lines. On the other hand, max margin solution is going to be always unique. Is that clear? Okay, so now this is good. So we solved the first issue with Perceptron, like the first major issue, which is the issue of having multiple solutions, right? But there is a more crucial issue, which is still not addressed, which is the issue of overlapping class distributions. Okay, so if my problem is linearly separable, max margin classifier is perfect, right? On the other hand, in reality, most of our problems are going to be not linearly separable. If your problem is not linearly separable, then you can see based on this error function that the error of max margin classifier is going to be infinite, right? Like it's infinity if the constraint is not satisfied, and it will not give you any solution, right? But in reality, like we want a classifier, even if the problem, like we want some classifier which works irrespective of whether it gets 0 training error or not, right? So now how do we do that? So like how do we deal with overlapping class distribution? So that is what we're going to discuss for the rest of the lecture. But maybe before that, is there any questions on max margin classifiers? If you have any questions, you could either type it in chat or raise hand. Okay, no questions. Is everything clear? Okay, so then, well, I doubt that, but maybe let's continue. Okay, so now we're going to look at overlapping class distributions. Okay, so now what's the issue with max margin classifier? The issue with max margin classifier is it assumes that the data is linearly separable. Okay. Now, what to do when data is not linearly separable? Okay. So, any suggestions? What can I change in this max margin formulation to deal with the case that the data is not linearly separable? Well, I think this you can answer. So, it's, any suggestions on how to improve this max margin classifier? Okay, so there is one suggestion, which is you find the minimum error than maximizing the margin. That's a good point, but you look at the error that we have, the error is just 0 or infinity, right? And this error that max margin classifier is trying to minimize is not a useful error. So we need to do something else to handle with max margin. Okay, have a constraint that is not linear. Well, that is not going to help you, right? So any other suggestions? Okay, so there is, okay, so there are a couple of good suggestions. Like, so one is like, how about we relax these constraints, right? Like, so why do I need this hard constraint which gives infinite value, right? Like, so also the related suggestion is like, instead of having infinity, right? Like, so we need to modify this error. Okay, so like the first sort of suggestion is a valid suggestion. Like we need to work on the error function, right? Like, and like the way in which we could do that is instead of having an error function which gives infinity, which is useless, we could actually have an error function which gives a large value for violations of the constraint, and then try to minimize this value, minimize this error as much as possible. Okay, so that is what we are going to do now. So what are we going to do? So we are going to modify the approach. Okay, so that the data points are allowed to be on the wrong side. Okay, are allowed to be on the wrong side of the margin. However, we are going to define a linear penalty based on how far they are from the margin. And instead of trying to just trying to maximize the margin, like we will have like a combined objective where we will also try to minimize this linear penalty. Okay, so how are we going to introduce this linear penalty, right? Like, so the way in which we are going to do that is what is known as the idea of slack variables. Okay, so I'm going to define a specific slack variable epsilon n, which is greater than or equal to 0 for all the data points. Okay, now this slack variable tells how much you can slack in the constraint, like how much you can go deviate from the constraints. Okay, so if epsilon n is equal to 0, then that means this is basically 0 for data points that are on or inside the correct margin boundary. So if a data point is in the margin or inside the margin, the error is given, the epsilon is, the slack variable is 0. Okay. On the other hand, epsilon n is defined as absolute value of t of n minus y of xn for other data points. Okay, so now let's look at an example. So here is an example where we're going to consider this margin. Okay, so this margin epsilon is equal to 0. If a data point lies in the margin, epsilon is 0. If a data point is inside the margin, epsilon is equal to 0. Okay, and now remember epsilon n is equal to t of n minus y of x. Right? Now let's say this is class +1, this is class -1. Okay. Now if a data point lies in between the decision boundary and the margin, okay, then that epsilon is going to be less than 1. Okay, because it is 1 minus some positive value, which is less than 1. Okay, so this whole thing is going to be, so this is value between 0 to 1, and the whole thing is going to be less than 1. Okay, on the other hand, the moment the data point crosses the boundary, so now this is an example of a wrong, the blue after the red line, like on the top of the red line, is an example of a wrong data point, right? So for this data point, its actual T of n is 1 minus the y value is going to be a negative value. So the whole thing becomes greater than 1. Okay, so to put it simply, I'll erase all these things. So now this is epsilon is equal to 0. This is the region where epsilon is less than 1. And this is all the region where epsilon is greater than 1. Is that clear? So now the moment I have such a slack variable formulation, now I can replace the exact constraints T of n, y of xn is greater than or equal to 1 with minus epsilon n for n is equal to 1 to n. Okay, so instead of having the exact constraint, I'm going to have this additional slack variable here. Okay, so now we have already seen the situation here, right? So if epsilon n, there are three possibilities. Epsilon n is equal to 0, or it is between 0 and 1, or it is greater than 1. Okay, so now we are going to do a small poll. Okay, so if epsilon n is equal to 0, okay, now is that data point correctly classified or wrongly classified? A for correctly classified and B for wrongly classified. Okay, so this is for epsilon n is equal to 0. So let's do the template poll. A for correctly classified and B for wrongly classified. It's a short poll. I will stop the poll in exactly 10 seconds, okay? Because I'm going to do the poll for all the three. Okay, so, well, 77% of you think it is correctly classified. It's actually correctly classified, right? Like, because we see that epsilon is equal to 0 only for examples in the margin or inside the margin. So they are safe, right? So now this is actually correctly classified. Now I'm going to ask the same question again. Now for data points between 0 and 1, for which epsilon is between 0 and 1. Okay. So now if you look at the data points which are between 0 and 1 epsilon, now these are data points which are outside the margin, but they are still within the decision boundary, right? So this is also going to be correctly classified. Okay. Now, instead of doing the poll, I'm just going to ask you to think about it. So what happens if epsilon n is greater than 1? So epsilon n is greater than 1 means that data point has crossed the decision boundary. Now, even though this specific blue color example should be within the decision boundary, it is outside the decision boundary. So now this is not correctly classified. Is that clear? Okay. Okay, there is a question. Classification is correct even if epsilon n is equal to 1. Yes, even if epsilon, okay, that's a good question. So if epsilon n is equal to 1, you are in the boundary, exactly. So it's 50-50. So probably it's a tie, right? So it depends on how you break the tie. That's a good question. There's also another question. Is this also used for linearly separable data problems? Okay, can we also use this for linearly separable data linearly separable data problems? Okay, can you remind me this question like when we finish the discussion so that it's more useful? Okay, okay. So now what have we done here? So we have basically took the hard margin constraints. The initial constraint said all the data points should be within the margin, right? But we took this hard margin constraint and we have converted or relaxed it into soft margin constraint. Okay. However, an important note about the limitation of this formulation. Okay. So this problem, the formulation has a problem. This is sensitive to outliers. Okay. Why? Because the penalty increases linearly with epsilon. So if I have like, okay, I'm trying to find this color. Okay, so this blue is very difficult to find. Okay, I think I found the color. Okay, so I was trying to find the blue color. Okay, so now let's say there is one specific blue example which is so far in the left side, in the wrong side. Okay, now this is supposed to be +1 example, but this is in the wrong side so far. Okay, maybe this is an outlier. Maybe this is error in the data set, or maybe this is like some measurement error, right? Like so it could be a noise, right? So on the other, but the formulation that we currently have is going to give very high penalty for this particular data point, which is going to have like a very huge error value or the loss value. You might think that your model is doing very bad, but it is just that there is one culprit who is an outlier. Okay, so this is something that you need to be very careful if you're using this model. Okay, so now let's write the objective function for this max margin, soft max margin formulation. Okay, so the goal here is maximize the margin while softly penalizing points that lie on the wrong side. Okay, so how do I do that? All I have to do is minimize the slack value as much as I can while I'm maximizing the margin. Okay, so you minimize some c times summation over n is equal to 1 to capital N epsilon n. Okay, so now you are minimizing the slack variable. Okay, and plus 1 over 2 w square, which is the usual thing that we already had, right? So where the parameter c is greater than 0, right? So this parameter is known as the cost parameter. Okay, and this controls the trade-off between slack variable penalty and margin. Okay, if you care so much about the margin, the cost will be less, which means the model will not tolerate a lot of violations. On the other hand, by tuning this cost parameter, you could actually decide the number of violations that you want. Okay, so now a quick note. So for any misclassified point, epsilon n is greater than 1, right? So summation over n epsilon n is basically an upper bound on number of misclassified points. Okay, so now if c goes to infinity, then we basically get the earlier max margin formulation. Okay, so if I set c to infinity, then it means epsilon has to go to 0. So everyone should be within the margin. So then basically the previous version that we discussed is a special case of this soft max margin problem. Okay, okay. So now I can actually write the primal problem for this soft version or the relaxed version. Okay, so the primal problem is given as arg min. Okay, now instead of just w and b, we also have epsilon. C times summation over n is equal to 1 to n epsilon n plus 1 over 2 w square subject to a bunch of constraints, right? Subject to the first constraint, which is T of n, y of xn should be greater than or equal to 1. If you just leave it like this, that's the earlier formulation. Now we have a slack added, n, where n is equal to 1 to n, right? And we also have additional constraint, which is epsilon n is greater than or equal to 0 for n is equal to 1 to n. Okay, now this is the primal formulation. Okay, now given that we have already done the whole thing before, right? Like so we are going to directly write, like we're going to directly jump to the Lagrangian formulation too. Okay, so the Lagrangian formulation is given as L of W B epsilon. Okay, and we are going to have some other parameters for the Lagrange multipliers. Okay, so this is basically 1 over 2 W square plus C times summation over n is equal to capital N epsilon n, right? Minus, so the first constraint is we are going to use A for Lagrangian multiplier. N is equal to 1 to n. We are going to have an times T of n W transpose phi of xn plus b minus 1. See, you are bringing 1 minus 1 epsilon to the left, so it becomes minus 1 plus epsilon n. Okay, and the second constraint is just epsilon n is greater than 0, right? So minus summation over n is equal to 1 to n mu n epsilon n. Okay, there are a lot of mistakes, notation mistakes in the notes for this, like, so please correct them. Okay, so now where we also have mu. Okay, an is greater than or equal to 0, mu n is greater than or equal to 0 are Lagrange multipliers. Is that clear? Any questions so far? Any questions before I continue? Okay, so no issues. Okay. Okay, so now I will directly write the corresponding Kkt conditions for this problem. Okay, so we have the similar one like before. An is greater than or equal to 0. T of n, y of xn minus 1 plus epsilon n is greater than or equal to 0. And either of them has to be active constraint. So either A of n is equal to 0 or T of n, y of xn is equal to 1 minus epsilon n, right? So similarly, for the second set of constraints, we have mu of n is greater than or equal to 0, epsilon n is greater than or equal to 0, mu of n epsilon n is equal to 0, where n is equal to 1 to n. Okay, so now I can actually do gradient descent with this specific thing, right? So I'm going to copy this and then find the value of W and like everything else other than the, what's it called? Everything else other than the Lagrange multiplier, then that gives us the dual, right? So I'm going to copy this. I'm going to copy this here. Okay, probably minimize it a bit. Okay. Okay, so now what is dou L by dou W is equal to 0, right? So the first term W, there is no W in the second term. So it looks very much like the previous solution, right? Like, so now this becomes minus summation over n is equal to 1 to capital N, an, T of n, phi of xn is equal to 0. So W becomes summation over n is equal to 1 to capital N, an, T of n, phi of xn. So this is, let's call this 7. Like, this is exactly similar to the previous one. Then we have dou L by dou B, which is also, there's nothing extra in terms of B here. So it's the same solution. So this is also summation over n is equal to 1 capital N, an, T of n is equal to 0, right? Let's call it 8. Now we have a third variable, epsilon, which is also something we need to remove, right? So dou L by dou epsilon n is equal to 0 implies, so epsilon n is in the first term here, right? So there is a cost involved. Then there's an epsilon n with respect to an. Then there's an epsilon n with respect to mu n. So basically C minus an minus mu n is equal to 0. So this means an is equal to C minus mu n. Let's just call this as 9. Okay. So now this, let's just call this as equation 6. Okay. So now I'm going to substitute 7, 8, 9 in equation 6. Okay. I'm not going to do the steps here. It's trivial. So you could do the steps and then you will find that it is exactly the same as the previous solution. An, am, tn, tm, kernel of xn, xn. It's exactly the same as the original hard max margin solution, except for the constraints. Okay, it's same as old solution, except for the constraints. So now what are the constraints? An is greater than or equal to 0, and mu n is greater than or equal to 0, right? Now using these two in the 9th equation, you'll find that an should also be less than or equal to c. Okay, so now we have what is known as the box constraint for an. An should be between 0 and c. Now this is the only change that we have. Okay, so now my dual formulation is given by maximize the L of A subject to 0 less than or equal to a n less than or equal to c for n is equal to 1 to n, and summation over n is equal to 1 to n, a and t of n is equal to 0. Right? Now this is my dual problem for the soft max margin classifier. Okay, so now let's try to interpret the solution. Interpretation of solution. Okay, now the first case is when a of n is equal to 0. When a of n is equal to 0, we have already seen that that data point is not going to be used. It's thrown out, right? So that data point is not used for prediction. Good. So then we have case 2, which is a of n is greater than 0. When a of n is greater than 0, then by Kkt condition, t of n y of xn should be equal to 1 minus epsilon n. Right? Okay. Now there are two possible scenarios here. Okay. So case 2a is when a of n is greater than 0 and it is actually less than c. Okay. So if it is less than c, then by equation 9, like if you remember this equation, mu n should be greater than 0. Okay, if mu n is greater than 0, then again by Kkt, epsilon n is equal to 0. Okay, so this means that such points lie in the margin. So if an is between 0 and c, those are the points which lie inside the margin. Okay, and now there is a final case, like the second part of case 2a, which is an is greater than 0 and an is actually exactly equal to c. Okay, now this thing lies inside the margin. Okay, and can either be correctly classified if epsilon n is less than or equal to 1, or misclassified if epsilon n is greater than 1, depending on what is your epsilon n. Okay, so what we have done here in the second half is basically, instead of having a very hard margin, we had a soft margin, which allowed us, okay, so can C be equal to 0? Well, if C is equal to 0, then you are going, well, that's actually very bad, right? Like, so, like if you go back to the primal, you can try to answer that by looking at the primal. So if C is equal to 0, then you have no constraint on minimizing the error. So that's not a useful problem. C has to be positive. So higher the value of C, larger the tolerance. Sorry, like higher the value of C, smaller the tolerance. You want the error to be minimized aggressively. Okay. Okay. So now this soft max margin formulation that we discussed, right? So this has a name. This is a famous algorithm. So this is known as support vector machine, or SVM. And what we discussed in today's lecture is actually a special version. Look, it's a linear SVM. Okay. And there are also nonlinear versions of it. And we will probably discuss how to make it nonlinear in the future lectures. Okay. Now there's a question. So what is the error function that the soft max margin classifier is trying to minimize? Okay. So what is the error function that the soft max margin or SVM classifier is trying to minimize? So now to give you an idea, the hard max margin classifier, right, was actually minimizing, the hard version was actually minimizing summation over n is equal to 1 to n e infinity of t of n, y of n, I think minus 1, right, like plus lambda times b squared. Is that right? So it had like infinite error when y of n, t of n is not greater than or equal to 1, right? So this was the hard version. Now the question is, what is the error function that the soft max margin classifier or SVM is trying to minimize? But probably, well, I would leave that as a thinking exercise, and probably we will discuss that in the next lecture. Okay, so I would like to stop here so that we have time for discussing our feedback. So let me stop the recording. Or maybe I'll take one question. So is there one or two questions? Is there any question before I stop the recording? Okay. Now good that you are reminding the problem, the question again. So can we use this for linearly separable problems as well, right? So yes, you can use it, right? Like, so now we saw that you are going to have this error only when the data is not linearly separable. If the data is linearly separable, the error is going to be 0 for the slack epsilons. The slack error is going to be 0. So yes, you could use it. Any other questions? Okay, so there's also office hours after this, so you could ask more questions there. So I'm stopping this recording.